right. All right. Okay. So one key observation is that our society functions thanks to oil and natural gas. And the second one is that global economy, because of that, because the society function on oil and gas, so then the global economy depends on oil and gas business quite a bit. There is no oil and gas business without fluid flow. So we are going to get busy with physics of the flow, but the general picture is that that is really at the crux of the oil and gas business. And motion, or this fluid flow, or flux, as we will actually define it later, occurs whenever there is a gradient of some potential. In our case, it's mostly, well, for the momentum, it's mostly going to be pressure. Okay? But you could also say that on a philosophical level, if there's gradient in society, some motion in society will happen as well. All right? And we'll actually have an example of that. So how much oil is it that we actually have to transport as an industry, that we have to transport around? What was the approximate world crude oil production in 2014 in million oil barrels per day? Any ideas? 90 million? Any other guesses? That's fairly close. I found the number of 78 for 2014. Okay, so 78, and this is breakdown by country, and this is this other gradient that I was talking about. So essentially, you have most recently, because of the shale gas, U.S. has surpassed Saudi Arabia. That is the current tug of war in oil prices. Because if the Saudi Arabia doesn't reduce their consumption, then that basically affects the price, and price has been falling down. So that's essentially where we are looking at it. Everybody's like, falling prices. Do you know that there's a current for? I hope so. Okay. So everybody's like, what is she talking about? So, welcome to petroleum engineering. First information you should find out in the morning, and that energy information website, administration website is one place to look it up, is what is the current oil price for the day and how different it is from a month ago versus how different it is from a year ago. And right now I think we're $50 different from a year ago. So business was pretty good when we were in hundreds of dollars. Right now we're in 39 or 38 is roughly the number. Okay? 45 today. There we go. One person is checking. I checked yesterday, and today I was just too busy to check. So, all right. So basically, that is what is causing some of the prices. So those are some social gradients that can drive different other forces in the economy. And then we have Canada, China, and United Arab Emirates now. So basically, if you just want to visualize that, I tried to run a quick calculation, and roughly one Olympic-sized pool is 2.5 million liters, which is this much in gallons. So if you actually convert that, then you need to fill up, this is Jamal's swimming center here at UT Austin. Basically, you need to fill up 2.5 of these pools every minute. So that's quite a bit of production of oil every day. So this is another way to look at those social gradients when you have largest consumers that don't overlap with largest producers. Then there are gradients and exchange needs to happen, and that's what's actually driving the economy. So I'm not going to go into the politics of oil prices, but one does have to recognize that we really depend on these driving forces in economy as well as the physical flow of fluid. Okay. Now, we flow and transport oil and gas in all kinds of ways. A lot of it is going through pipes. Sometimes, of course, we transport it with other means. And it's the pipe that we're sort of, in terms of engineering, petroleum engineering, we're going to mostly focus on designing pipes. And pipes you should be familiar with. So if I have a gradient in pressure in a pipe and I have a Newtonian liquid in there, how about each and one of you do a little calculation just to start your brain. So I have a tube of length 250 millimeter, and its diameter is 5 millimeter. And pressure gradient is 1 kilopascal per meter. How much force in the direction of flow does this liquid exert on the tube? This is just to recall whatever it is that you studied during your undergrad. So regardless what the number is, what is the approach to this? I actually don't know what the number is, I forgot. Okay. What are my ways in solving for this? Most of you probably know a formula, okay, some formula. What are the formulas that you know? What do they relate? Typically you will actually know, so the most detailed way we could know is to solve for the flow in the entire tube, right? And then since I'm actually asking for the force in the direction of the flow that I exert on the tube, I would probably have to integrate stress on that surface, right? So I would have to figure out what the stress is and integrate it, right? For the tube, we will be actually able to find a closed formula that then just gives me that stress. And what physically it ends up being, it can actually be related on the pressure difference that it gets exerted on this face. That is not necessarily, because there is a balance of forces, right? Okay. There's certain force that basically is just here acted on this face of the tube. And because of the balance of forces, it's actually equal to the force in the x direction that is exerted on the sides of the tube. So we can actually relate that. Okay. So part of this course will be actually to find these relationships. Some of it you could actually do by this microscopic balance of forces. I have forces in x direction, and I can equate what they are, what they should be, on the macroscopic level, just on the level of the tube, right? Or I can have sort of microscopic solutions, so I know how my entire flow field looks like here. I can find the stresses, I can integrate them, and do it that way. There is a benefit in both approaches. Okay? If I, in an engineering way, approximate my world by pipes, and I have the closed form solutions for pipes, that's very valuable. was our class done? the bell is still off. So if I can approximate my world with pipes, we will learn a whole lot of analytic solutions for pipes. Okay? And those are valuable in the sense that I can use them off the bat because I can just plug things in and calculate. However, my world might not be as pretty as pipes, and I might actually have something. I'm just gonna go on. So these would be, for instance, pipes that we engineer, okay? And those pipes are obviously straight, and we have engineered them. We know everything about them, and we can actually compute something quite a bit. So this is Trans-Alaskan pipe, and this is actually the pipe network in the United States for natural gas, okay, pipelines. Okay. So in those, we can obviously compute easily, okay? Now we can have all kinds of pipes, and the pipes that I love looking into are those that are actually in the microstructure of the rock itself. So if you zoom in, this is a rock you could be walking by. You take a core out of it, and you zoom in with microscopic vision, or X-ray vision rather. So this is X-ray slice. This here is 1.25 millimeter, zoomed in with about 5 micron resolution. I can see pore spaces in between grains. This is a Berea sandstone. Okay? So I have to have quite a bit of imagination, and people do. So we approximate this space in 3 dimensions as a network of pipes as well. Okay? Now, of course, I'm ignoring inertial flows in the corners of the pipes if I'm actually fitting in a tube through this space and approximating it as a pipe. But if I'm interested in the details, okay, we will actually develop general formulas that you would have to build a method to solve in this type of space if you're really interested in the detail of what is the force that fluid is exerting on the side of this sandstone. So in your research, you will go somewhere in between. You will pick how much of an approximation or simple solution are you going to go for, how are you going to simplify your world. But 2 things that you should get out of this course in general are, one is, what is the simplification? What is the key simplification of my problem that I can make? One example of it is if I'm water flooding a reservoir and I'm interested in time of arrival, okay, of my front to a point in space 100 meters away, okay, or from one well to another. Am I going to be modeling advection or diffusion? What's important? Is diffusion important for first time of arrival? I don't think so. So I need to know the dominant mechanism that is guiding whatever it is. So that's already reservoir engineering. But basics of it we're actually going to cover in this class. What is the dominant mechanism? Can I actually then simplify? So I can go and spend an entire PhD, figuring out a great solver for diffusion, but if it's not going to help me in that problem, then I have wasted my time. So that's the first engineering decision that you have to make is, how do I simplify my problem? Can I decouple it? Can I look at the advection first and diffusion later? Can I look at the advection in X direction and diffusion in Y direction and decouple it that way? And because of the decoupling, I can possibly find an analytic solution. Right? So what are the simplifications that we can make? And is tube a good approximation for my problem? If it is, I'm really happy. I can actually even work with some analytic solutions. So even if later on I'm going to build a solver to do that, or use software to do that, I know how to calculate an analytic solution to check against. It's very important that whatever it is you do in your research, first step you will have to prove is that you can trust your product, whether that's an experimental or a simulation product. Right? You will have to prove it in the paper that it works. In some simple cases where we have an analytic solution. So this course will provide you with an array of analytic solutions, and hopefully you will learn the process of how do I simplify my problem down to something that I can solve. Okay? Mostly pipe, annulus, slit. Those are the 3 main geometries that you will need to know inside and out. Okay? unfortunately, and around the sphere. And unfortunately, there is difference in coordinate systems that you use for the three. So that's going to be the source of friction here. Okay? So these are the small pipes. And then, of course, you fill those pipes with different fluids. And this is, for instance, an X-ray of sphere packing. These are the spheres, and there are three orthogonal views. This is air. This is water. So you can see how two different fluids compete in the pore space. And so this is what I personally do for research quite a bit. And you can see this curved interface in between. So I need to overcome the capillary pressure here, the capillary pressure barrier essentially to push through. And that's essential problem displacement. In this course, we will not get the luxury of going too much into two-phase flow. We will mostly be in single phase. Okay. This is just another example where I don't have just two fluids, but I actually have oil, water, and air. So I have three, which is a common situation, of course, in petroleum industry to have three fluids competing for the same space, and that is causing all kinds of issues. So my permeability now becomes relative permeability that depends on the saturation of each fluid. And again, this is all advanced reservoir engineering stuff, but it is related. Ultimately, you have to start from single phase flow that we're covering in this course. And then just to continue that quiz, and this is actually just for your own amusement. And I'm not going to provide the answer, you're going to actually provide it for yourself. So this is a similar problem to that first one. And it's just now that my tube has a curve. Pressure gradient is the same. Length is the same. Diameter is the same. And I'm asking whether this force in the x direction exerted by the liquid on the tube is greater or smaller than the force in the previous question. So think about it for a moment, or for the weekend if you want to. So I'm going to let you figure that out and prove yourself right or wrong. What I'm really exemplifying here is that often we don't necessarily learn from the actual answer. I actually didn't bother to actually look up what the answer was for either of these here. Okay? We learn by comparison. So if I have a system that I already have no solution for, can I, this new situation that I'm having, how does it compare? And again, in your research, you'll have to do that too. So you'll have to start from what's already known and what's already out there. Okay? And that's your starting point. And whatever it is that you do, you have to motivate, how is it important, okay? If it's this much smaller, or this much greater, or this or that, how is it important and why it is that you need to study what you need to study? So in this whole process of both how do you build the method and how do you compare what's out there, I have just outlined your preliminary exam. Okay. So you'll have to propose a problem that is important, and you'll have to do a literature review to compare to what's out there in the literature already, and why does it make sense for you to propose the research that you're proposing. Whether it's your master, well, in masters you don't have to do a preliminary exam, but for the research you do, you still have to know why you're doing it. So you just don't go through the exam process. And everybody's giving me these looks. What is a preliminary exam? What is the preliminary exam? What is qualifying exam? Qualifying is the written exam in 3 subject areas that you're taking in order to move on to the PhD. Right? And those 3 areas are transport, engineering analysis, and petrophysics. Right? After that, you're still not a PhD candidate after that. To become a PhD candidate, you have to defend a preliminary exam in front of a committee. So you have to form a committee, find the topic of study, do literature review on that topic, and also do some preliminary result in whatever it is that you start research-wise on it. Okay? And then you have to defend in front of the committee and say, why is your topic important? How does it compare what's out there in the literature already? And what are your proposed methods to study that topic? And committee then says, yes, this sounds like a good plan, or this doesn't sound like a good plan. Okay? That's why it's an exam. So those are the important things to think about already. So yes, you will have a busy semester. For those of you who are trying to do PhD, you will have a busy semester just in courses, but do read the papers for your research too and start thinking about this and putting things into context, because whatever you propose to do has to be new. It cannot be something that was already there. So in these two basic questions, but that's a basic question of scientific inquiry as well. Okay. Being in engineering, you should study an important problem. Now, what's the currently really hot topic in the United States is these nanotypes, okay, nanoscale. So if you have organic shale or mud rock is a very fine-grained rock, and it often has both silt or mud or basically silica part and organic content mixed together plus some clay. So that mixture makes it for a whole lot of fun. Those organic matter pores that we actually depend on for extracting oil and gas, they can be in 5 to 750 nanometer range. Nanometer is 1,000 times smaller than micrometer, and most of the sandstone pores are micrometer level. So these are 1,000 times smaller. And because they're 1,000 times smaller, basically their permeability of such a rock will be 1,000,000 times smaller. Okay? So we will get to actually proving that relationship for some simple rocks, okay, where my permeability depends on the grain size squared. So if my grain size is reduced 10 times, my permeability is reduced 10 to the square, 10 square times. Okay. So that's one of the basic insights that we're going to do. That is essentially petrophysics insight, and that it's just that in petrophysics you don't prove it, we prove it in this class, okay, because we have the tools here. So essentially, it is a problem if suddenly my permeability is that much smaller. I have a production problem, and there's a lot of research going on. It's even a problem to see stuff that is on a micrometer scale. Now, if I need to see nanometer scale, of course, it's challenging, and my imaging tools have to be very advanced. But with the advanced imaging tools, I'm going to go smaller, but my field of view is smaller too. So suddenly I'm saying something about 10 micron square area of the rock. That's very small, okay? And that is the challenge. And these rocks are very heterogeneous, so that right now it's an ongoing problem how to describe them and how to describe their flow properties. Nevertheless, the motivation is there. So this is 54% of natural gas comes from tight shale and coal bed method. Okay. So there's a lot of research going on in this department. And again, for this, one of the basic assumptions that we are actually going to look at in this course, we're going to actually move up and down different scales. And this is actually from your textbook. Okay. It's right here. This motivation is right here. So the origin of most of the phenomena that we're going to look at is molecular. But molecular scale is too small for us to actually resolve flow of interest if I need to flow something from pipe in Alaska and across Alaska, right? So I have this kilometer scale that I have to figure out. However, the essence of friction, okay, between the different layers in the fluid is in essence molecular. So we will actually go and try to go up and down these scales to describe things in various ways. When we're actually resolving for flow, okay, the detailed equations will be on the microscopic level, okay? And then from those equations, we will come up with sort of engineering solutions on the macroscopic level, okay? So essentially, and we will explain things on the molecular level. So that's how we will actually go up and down different scales. So our key assumption will actually be that yes, we know matter is actually molecular and composed of molecules, but in many applications, the number of these molecules is large enough that I can just take off my glasses and not see much. If I take off my glasses, I don't see you all very well. So that comparison essentially works. So I'm just going to see how do you behave as a continuum. And basically, I have large number enough that I can speak of continuous phases. Okay? And we can solve successfully a lot of problems assuming that matter acts as a continuum. Okay, so that's our equations will work on this continuum level. So everybody has heard about Navier-Stokes equation. So it's a continuum equation. If I didn't have that in continuum equation, I would have to go to molecular dynamics and basically molecules bouncing into each other and exchanging momentum. Okay, and that decides where they're going to be. But I don't always want to track down molecules. But now I'm going to actually cue in back this shale problem again. If I actually indeed have a 5 nanometer pore, okay, and my average molecule is what? Let's say 3 angstrom. Okay. 3 angstrom into 5 nanometers. Let's say 5 angstrom into 5 nanometers. Difference is 10. Okay. So if I have a channel that can fit only 10 of my molecules across, and larger molecules, let's not even go there, like larger molecules can get even larger, then I might be on the borderline of this continuum assumption. So that's actually what's happening now in research. There's a whole lot of research. Well, how do we adjust the formulas that we know that are working on them? If I have a micrometer channel, then I have 5,000 of these molecules across. That's fine. But if I have only 5, my continuum assumption is breaking down. And because it's breaking down, I need new formulas. I cannot use my old knowledge. If I want to figure out now also gas in place in something in the system like this, okay, what's happening is that I also, as I'm packing things in, and I'm adding so diffusion actually becomes important and not just advection in these spaces. Okay. My flux through does not depend only on the gradient of the pressure, but it depends on the pressure itself. Whether I have my gas in liquid or gas phase depends on the pressure too. And with different pressures and packing structures, I will change phase. Okay. There's a whole lot of things that I have to actually suddenly look into, and that you will possibly look into in your research, just because I'm breaking down the continuum assumption. Okay. So everything that you learn here, know what the limits are. Whatever model you come up with, whatever formula you come up with, you have to know the simplifying assumptions that went into that formula and not apply it blindly. Because you're getting an advanced degree as opposed to just bachelor's degree. With bachelor's degree, you can just go and do the formulas without thinking too much. But with an advanced degree, you're now kind of forced to think through and say, well, okay, what were my assumptions and what is the range of validity of my formula? Formulas are nevertheless still useful, okay? They allow you to compare different cases, even if it's in a simple pipe, you can still learn a lot. So having models and formulas is a vehicle for thinking. Okay? They're never going to be absolutely correct in no circumstance, but they're nevertheless really helpful, and they can still guide your intuition. So yes, we'll go through quite a lot of trouble to develop fairly simple relationships, okay? And their range of validity is not going to be super broad, but they're nevertheless, if you know where to apply them and apply them correctly, you can nevertheless learn a lot. Does that make sense? From the philosophical, big picture level. All right. Okay. So how do we build up across scales? That's kind of what the science is about, coming up and confirming laws. And this process of scientific method, I'm going to actually emphasize now with the words of Feynman. And I'm just going to motivate you before I play you this movie. I'm going to motivate you to think about it also in terms of like, how are you going to do research? Okay, how are you actually going to come up with a good topic? So I'm going to play this. Everybody knows who Richard Feynman is? Physicist.
Now I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature. Or we say compare to experiment or experience. Compare it directly with observations to see if it works. If it disagrees with experiment, it's wrong. In that simple statement is the key to science. It doesn't make a difference how beautiful your guess is, it doesn't make a difference how smart you are who made the guess, or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
So
It's therefore not unscientific to take a guess, although many people who are not in science think it is. For instance, I had a conversation about flying saucers some years ago with laymen. Because I'm scientific, I know all about flying saucers. So I said, I don't think there are flying saucers. So my antagonist said, is it impossible that there are flying saucers? Can you prove that it's impossible? I said, no, I can't prove it's impossible. It's just very unlikely. That, they say, you are very unscientific. If you can't prove it impossible, then why, how can you say it's likely, that it's unlikely? Well, that's the way that is scientific. It is scientific only to say what's more likely and less likely, and not to be proving all the time possible and impossible. To define what I mean, I finally said to him, listen, I mean that from my knowledge of the world that I see around me, I think that it is much more likely that the reports of flying saucers are the result of the known irrational characteristics of terrestrial intelligence rather than the unknown rational efforts of extraterrestrial intelligence. It's just more likely, that's all. And it's a good guess. And we always try to guess the most likely explanation, keeping in the back of the mind the fact that if it doesn't work, then we must discuss the other possibilities.
that's essentially so just to bring up the key points. You guess, that's your scientific hypothesis, that's the fancy word for a guess. You make an educated guess based on what's out there already. Then you compute, and then as he says, compute the consequences and compare to the experiments, either existing theory or experiments, that prove whether your guess works and what are the limitations on your guess working. Okay? And again, you're not proving possibility or impossibility. Science is somewhat incremental in the sense that typically we work by comparison, and that's that comparison that I tried to highlight earlier. You compare what's already out there, and in that sense, models are really useful because they allow you to compare, as in quantify and compare. Something is more beautiful versus less beautiful doesn't work in science, okay? But I know how to compare 10 and 20. Okay, so we need to quantify in order to compare. But Feynman is funny. You can find a whole lot of movies on YouTube. That's what I do in my pastime. So basically, we will actually postulate conservation of mass, momentum, and energy. And in time and space that we're working with, they're very good postulates, and we will build from there. Now, our key tool in this whole endeavor in transport phenomena will be conservation equations. So basically, these conservation equations that we will solve, they result from applying these laws that we find sensible. Conservation of mass is a sensible law. And we apply it on different scales and on different coordinate systems or different geometries. And those are the tools that are essential kind of language of transport phenomena. So we will look at the mass of a phase, mass of a component in one or more phases. So this is basically mass transport, and then heat, energy, and momentum. So you can actually amuse yourself with some more movies by Feynman at your own time. And you will notice sort of similarity on the syllabus in this sort of process in moving across different scales, and also similarity between different types of transport, and that's the whole point of teaching this class this way. So if you look at the momentum transport, we first look at the molecular basis for viscosity, then we go through shell balances, which is essentially are going to give us the equations we need, and equations of change. And then we will also do a little bit of more tricky details that are going to be trying to solve problems in more complicated geometries. Namely, this is for around the sphere. And we will look at some non-Newtonian flow too, because of course the Newtonian flows are great. They're fairly simple to handle, but unfortunately they don't describe all of the fluids that are relevant in petroleum engineering. So if I have drilling fluid, where I have suspended mud, and that mud or little particles of sand are suspended with other, even smaller particles that keep them stable, that particulate system is not a Newtonian fluid, so I have to know how to approach it. Though most often we will still just assume a Newtonian fluid of some larger viscosity and so forth, because solvers become a problem for non-Newtonian fluid flow. We will divert into some porous media applications, so we will actually come up with Karman-Kozeny, or we will actually prove Karman-Kozeny relationship between the permeability and the size of a sphere in a sphere packing. And then we will look very briefly into macroscopic momentum transport. This one, given on the time, I sometimes cut a little shorter because the others are more fundamental problems, but it might nevertheless come up in your qualifying. Okay. And then we have energy in mass transport that follow the same routine. So we will look into the molecular basis for them. We will come up with shell balances and then equations of change. Okay, so shell balances we use for steady state problems where we don't have time. Equation of change are more general. And similar procedure for mass transport. And again, equations that we come up with will be similar in structure, and that's the whole point, like in terms of the computational tool, they're somewhat similar, and that's the whole point of studying all of these. So tool is kind of the same for all of these phenomena, even though they're across the spectrum in terms of physics or underlying physics. Questions? We're all good? Okay. So we have, let me just see. Yeah, so I have just a couple of minutes so I'm gonna probably be a little early, but I don't want to start another lecture. So just to go back to our observations on their relevance. So our motion or flux occurs whenever there is a gradient of potential. So whenever I perturb my system from the equilibrium state, I can expect some transport to occur. Okay? And that transport is trying to actually restore the equilibrium. So this disturbance is typically the change of some quantity that I'm looking into, and that's my spatial gradient that is driving the flow. So let's say if I have a temperature gradient, that would be the spatial gradient of temperature. And particles will typically move in the attempt to equilibrate these gradients. So one of the main relationships we're actually going to look into, and often this is the relationship that we could build from molecular to continuum assumption and have very rigid equations describing it. Or we could look at it in macroscopic world and simply do an experiment that will give me the same equations. So in terms of science, I could sometimes meet in the middle from two different ends. So I can either build equations from the microscopic side, or I could look from the macroscopic side in the lab and still come up with these relationships. Okay? So I'm going to look at the flux of particles as a function of gradient. Can you give me an example of that relationship that is the most common one in porous medium? Darcy's law. So flux Q is equal to minus some coefficients times gradient of pressure. Right? So that's precisely this relationship. Function of gradient in pressure. So this I'm modeling a vection here, right? And flux happens as a result of that gradient. Now what are my coefficients? Okay. K is permeability divided by viscosity. So the simplification I'm making is that I can separate the two so that my permeability is some sort of intrinsic property of my porous medium that doesn't depend on the fluid itself. And fluid is separated, and I'm just describing it by its viscosity. Okay? So that's the simplistic or simplifying assumption I'm making, and we actually know that's not true. Okay? We're also making a very simple assumption if I'm using it as a sort of a 1D type of thing. I'm assuming that this K is same in all directions. Okay? If I have a layered porous medium, I know that's not true either. Okay, so in Z direction versus X direction, it might be different. Okay? So there are I need to know what is built into that simplifying assumption. We will build that relationship in this course from scratch for a sphere pack, from the bottom. That's what I'm saying. We're going to start on microscopic level and actually come up with that relationship, okay, and measure it. In particular, we're going to come up with a formula for K for a sphere pack. Okay? But I could have gone in the lab, that's what Darcy did, measure fluxes, measure gradients, and hey, there's a linear relationship between the two. Okay? So that observation is the macroscopic observation, and you can meet in the middle, and science should meet in the middle. What it is that you're going to choose for your research depends on do you have a knack for one or the other? You know, do you like one thing or the other? But even if you pick one thing, you will have to compare with somebody else's research on the other. Right? So if you like experiments better, you're going to do that, but you're going to have to compare to the theory and computation that other people did in the other way around. Okay? But the science here needs all three of those. So basically, you need to know this functional relationship. So for starting reading so that you're not totally bored during the weekend, because I know you don't know what else you would do, right? So let's start with next book. There's a chapter 0 at the very beginning. Okay? And then if you're new to petroleum engineering, and some of you are, or if you need a text that will allow you to speak in simple terms about the complicated stuff you do in your life, you can go to oil and natural gas. There's a book, very colorful book. I have it in the office. You can borrow it if you want. Okay? That you can just use or order. And then for any kind of information on energy, you can go to this website. So that's your reading for this weekend, and I'll see you on Monday.